we are now going to discuss the second law, finally, second law of thermodynamics. The difference between the first law and the second law is that in second law of thermodynamics, we are going to discuss that there are certain processes na forbidden. Okay, so second law is what gives direction to your processes, whether they are spontaneous or not spontaneous. Okay. Let's start the discussion dito sa ating diagram na nakikita sa inyong slides. Okay, so let's say we have a hot reservoir, okay, or a reservoir with this hot temperature T hot, okay, and you want to extract energy from that reservoir. And the way you do that is kailangan mo ng isang working fluid and an engine to perform that extraction. So that engine could be a steam engine, so your working fluid could be the steam. Okay, so you want to extract energy. So therefore, heat is being transferred from this reservoir to the working fluid with an amount Q1. Okay, so you can do that. You can extract work from that heat and dissipate that work or apply that work to the surroundings. Okay, however, this conversion will not be 100% efficient. Okay, so not all of those heat transfers here will be converted to your work. So there will be waste of heat that will be dispersed, okay, to your cold reservoir. So in other words, we can actually calculate how efficient the engine is, okay, or the process is, by just knowing the temperatures or the operating limits of this system. So what will be the hotter temperature and what will be the lower limit or the colder temperature. So we can do that by computing, okay, or doing this computation right here, which is in order for us to determine the thermodynamic efficiency, it's simply the work you extracted divided by Q1. Okay, and it's actually, it can be computed based on the T hot and the T cold. So T hot minus T cold over T hot will be your thermodynamic efficiency. Ibig sabihin yung efficiency maximum na pwedeng ma-achieve ng system or ng engine. Okay? Let's say I have here another. Okay, so before that, we can probably answer this question. So let's have a steam engine in a power plant operating between 800 and 330 Kelvin. What is the maximum work that can be obtained from 1 kilowatt hour of heat? Take note that 1 kilowatt hour is equal to 3.6 times 10 raised to 6 joules. Okay, so since we know the upper and lower limits of the temperature, okay, we will be able to know the thermodynamic efficiency. Ibig sabihin ng thermodynamic efficiency, yung maximum efficiency possible for this engine. Okay, of course, in reality, you don't expect na ma-achieve mo yung efficiency na ito. Okay? It depends on the setup, the technology, how do you set up the cycle, and so on and so forth. So, you can calculate the efficiency by simply taking the difference between the temperatures and divide it by the hotter temperature. And we obtain here an efficiency of around 58.75%. Okay. And to calculate the maximum work that can be obtained with this particular efficiency, so you just have to multiply that efficiency by, ang sabi sa problem, 1 kilowatt hour. Okay? And again, if you want to obtain that in joules, so 1 kilowatt hour is 36 kilojoules. Okay? And so the work that can be obtained is 2,115 kilojoules. Okay, what if gusto mong mag-extract ng energy not from the hot reservoir but from the cold reservoir? Pwede ba yun? So yes, it's possible, but in order for you to do that, there should be a work done on the working fluid. So this working fluid could be probably a refrigerant like your Freon, and the system that can accomplish that, an example would be your refrigeration or refrigerator. Okay, so you can extract heat from the cold environment, but you need to input some work. So according to the second law, hindi pwedeng mag-extract ka ng energy from the colder environment without putting in some work. Okay? And that work, if you have the case of refrigerator, that will be coming from your compressor. Okay. We can actually evaluate the performance of this system or the working fluid, or as an example, refrigerator, by calculating what we call the coefficient of performance, or COP. Okay. How we are going to divide the heat input, okay, to the working fluid from the cold environment and the input of your work, okay, to the working fluid. And you can actually calculate that by simply using the limits or the temperature limits, okay, yung hot and cold. So T cold over T hot minus T cold. So that will be your COP. Okay. Now let's talk about entropy, because entropy is a property that is central to our understanding of the second law of thermodynamics. So entropy is the degree of disorder of a system. And the second law of thermodynamics states that the entropy of an isolated system must increase. Okay, so ano ba ang ibig sabihin ng entropy, and bakit gusto ng isang isolated system na mag-increase yung kanyang entropy? So let's take the case of a coin. Okay, so if you flip a coin, okay, ang tsansa na lalabas ay head 50%, kapag tail naman 50%. So 50-50. Okay, now statistically speaking, if you flip, let's say, 100 coins, okay, probabilistically, statistically, you can expect, kapag walang bias, okay, na 50 ang makuha mong heads and 50 ang makuha mong tails. Okay, so that's naturally what could happen, okay, probabilistically speaking. So let's say we just want to, flip 4 coins lang. So nature will dictate such that if you flip 4 coins, okay, the most probable would be that, again, if you are going to flip these coins simultaneously, so ang nature ididikta niya na dalawang head makukuha mo, dalawang tail makukuha mo. Okay, so why is that? Kasi the reason is entropy. Okay? And again, entropy is the state of disorder of a system, which is related to the number of microstates or conformations of a system. So let me explain. If you have 4 coins, okay, and let's say you want to expect na kapag tinos mo sila simultaneously yung 4 na coins na yun, and you are expecting na lahat heads ang makakuha mo, okay, yes, that's possible, but nature will not prefer that, okay, will not favor that. Kasi if all 4 coins land on heads, may isa lang na possibility, okay, isang possibility lang yun. Alright? But if, let's say, that, well, the reason kung bakit 2 heads and 2 tails ang kakalabasan, it's because of this. Okay? There will be 6 different combinations or states in which exactly half of the coins land on heads and of course the other half land on tails. So pwedeng so if this is coin 1, 2, 3, 4, so head, head, tail, tail, head, tail, tail, so head, tail, head, and then tail, head, head, tail, and then tail, head, then tail, tail, head, head. So 6 lahat ng possibilities. Unlike kapag ang expectation mo ay 4 pare-parehong heads, isang possibility lang. So there is more flexibility kapag 6 na different states. Kapag dalawang head, dalawang tail. So we can call this microstates if, of course, you're dealing with molecules. So we call this microstates. So there is a larger number of microstates kapag 50-50 as compared to all heads. Okay? So mas pinapaboran ni nature to kasi mas maraming possibility. In other words, the greater the number of possibilities or the greater the number of microstates, the greater the entropy. And nature favors that. Okay? The first person to describe entropy in this probabilistic statistical way is si Ludwig Boltzmann. In fact, yung definition niya ng entropy is statistical. Okay? And doon sa kanyang puntod, hanggang ngayon, naka-engrave yung equation na na-discover niya. Okay, so nakikita nyo dito sa slide yung S equals K log W. So W is actually the number of microstates. And if you increase the value of W, you will increase also your entropy. And K is actually your Boltzmann constant. Okay. So what else? We have here, if we're going to apply the same principle to describe the behavior of gas molecules in a 2-chamber system, shown here in this slide. Okay. In the initial condition, one of the chambers is empty. So ito yung empty chamber, and the other chamber, okay, is closed from the empty chamber, and it's filled with molecules. So there's a divider that prevents the gas molecules from entering this chamber. Okay. Now let's say we release this divider between the chambers. So what will happen is that the gas molecules here will undergo free expansion. Okay? So yung free expansion na yan, it occurs readily, but the reverse process, okay, will not happen. It will never be observed. So once these molecules are spread out into the chambers, the gas molecules will not suddenly collect themselves into the first chamber, okay, leaving the second chamber empty. Okay, so yung scenario na to, it's kind of similar to the coin tossing analogy. So at any moment in time, each molecule can be either in chamber 1 or chamber 2. Parang yung coin lang, di ba? Pwedeng head, pwedeng tail. But if we increase the number of molecules, the chances become less likely that all of the molecules will be found in one chamber. Okay? So let's say you're dealing with 1 mole of these molecules, and that's equal to 6 times 10 raised to 23 molecules. So yung chansang yun, okay, negligible siya. And we do not observe the molecule suddenly collecting into one chamber, at least during our lifetime. Okay? What are the other ways to increase entropy? So in chemical reactions, okay, we have this case wherein you have 1 mole of reactant. Ang tawag dito ay decomposition. So it decomposes into 2 moles of product. So that's a change, or that's an increase in entropy. Kasi kapag dalawa na yung moles ng products mo, so mas marami siyang probability of microstates or yung kanyang conformation, for example. Okay, same is true if let's say we have a cyclic compound and you suddenly open up by a chain opening reaction. Okay, so mas malaya, kumbaga, mas maraming conformation itong acyclic compound na ito. Okay, so that's another way to increase entropy. Okay. Now, si Clausius, okay, he figured out a way, or let's say, na-discover niya that we can calculate the entropy, okay, using a state variable, which is your heat. Okay, so according to Clausius, entropy can be defined as dq rev. Okay, rev here means reversible, divided by the absolute temperature. Okay, thus you can have your entropy, okay, with units, let's say joules per Kelvin or If it's a molar entropy value, it's joules per Kelvin mole. Okay, so that's how we calculate entropy. If you were going to calculate delta S, S2 minus S1, so just have to integrate that. Okay. Now, how do we define a spontaneous process? Sabi natin kanina, yung second law, it will dictate the direction of a certain process. Will it be spontaneous or not? So how do we know if a process is spontaneous? How do we know which processes are forbidden? So here is the entropic definition of a spontaneous process. And it says that the entropy of a system plus the entropy of your surroundings, okay, should be greater than or equal to 0. So if you somehow, let's say, yung entropy ng system, you can actually calculate that, right? Using yung formula natin. And even our textbooks would have values of your entropy, ng mga iba't-ibang processes like reactions, okay? Yung surrounding, it's quite difficult to measure the entropy of the surrounding, but let's say somehow you manage to get that value. So if you take the total, okay, dapat greater than or equal to 0 para malaman natin na spontaneous yung process. Okay? Now, what are some forms of entropy that we can use in physical and chemical processes? Okay, an example would be your phase transition. So, if to get the entropy of transition, so anong ibig sabihin ng transition? It could be transition from liquid to solid or vice versa, or liquid to gas or vice versa. In other words, yung mga phase changes, okay? So you can have entropy of vaporization, entropy of condensation, entropy of fusion, etc. So how do we calculate that? So just integrate again yung dq rev over t, okay? And that will now become the enthalpy of transition divided by T. So you can get the entropy of transition by getting the enthalpy of transition and divide it by the temperature absolute. Okay. Now let's say the process will be just heating or cooling at constant pressure. Okay. So karaniwan natin ito nakikita in the laboratory, right? Because normally chemical reactions in the laboratory are carried out at constant pressure. Of course, that's not true all the time. In fact, marami din namang reactions or processes that are carried out at varying pressures, especially in the chemical process industries. Okay, but kapag hindi siya phase change, but rather change in temperature with constant pressure, either heating or cooling. Okay, so again, delta S is you have to integrate the dq rev over T. But since constant pressure siya, diba, si dq, okay, is just equal to your delta H, and delta H is Cp dt if you have the case of an ideal gas. Okay, so I'm talking about an ideal gas here. So Cp dt over T, integrate mo lang yan. Okay. If you have the case of heating or cooling at constant volume, Cv dt over T naman yung i-integrate natin.